So it can get a little bit more into heat and temperature. So let's remind ourselves of the difference between heat and temperature. What are the definition of these things? The heat is the total molecular scale kinetic energy in a given substance. Again, that's just energy. It's going to have the dimensionality of energy. We're not going to break that energy down into motion, so I'm just going to call that capital E for now. Now, temperature is different. How is temperature related to heat? And what is the fundamental definition of temperature? Well, there are a couple of them. Sometimes the temperature is defined as the ability to conduct heat when you're specifically thinking about heat movement. But I think the most fundamental definition of temperature is the average kinetic energy of the molecules of a substance. So it isn't the total amount of energy they have, it's just the average energy over those molecules. Now, temperature has this fundamental dimension of a capital theta, but we can think a little bit more carefully about what that might mean when we use the equation that relates heat to temperature. And that equation is saying that the heat in a given substance is equal to the temperature times the mass of the substance times this property of the substance called specific heat. And then the specific heat tells you something about just how much energy it takes to change the temperature of a given mass of the substance by a given change in temperature. So we can rearrange this equation of this relationship to think a little bit more carefully about what temperature might mean. If we've got the heat in the substance over the mass of the substance times the inverse of the specific heat, we can write out the dimensions of each of those variables, that capital theta, E for heat, M for mass, and then the rest of that equation for specific heat. Well, this gives us, just thinking dimensionally about each of the variables in this equation, gives us some insight into what temperature really is. So if the specific heat of a substance is invariant, and you're just talking about a particular substance that has a given specific heat, and we sort of ignore the rest of the dimensions, you can see how this equation shows you that a temperature is basically like a density of heat. It's the amount of heat you have per mass of a given substance. So going through these dimensional analyses also help you think through what a variable might mean. And let's go through some more tricky examples to see how that might work. Like there's a weird unit in hydrology called an acre-foot of water. I'm not sure if you've heard of that before, but the idea is you have a given area of land in acres and a given depth of water over that land in feet. So when you say acre-foot, it's equivalent to saying acre times feet. Well, an acre is area, it's a length squared. A depth is, for the foot, is also a length, not also, it is a length. And when you take an acre foot, you're saying, well, it's acre times feet, that is a length squared times a length, that's a length cubed. So you can say, well, acre feet, that's a weird unit, but it's just a volume. And its dimensionality is length cubed like any other volume. So again, thinking about dimensions gets you away from worrying about these kind of weird units that you may not recognize if you can just figure out the dimensionality of the variable. Electricity is another interesting one. What do we pay for when we pay for electricity? If you look at your electric bill, what do you pay for? You're going to see this unit on there that says kilowatt hours. Well, this is another one of those units that is a multiplication implied, is a kilowatt times an hour. And kilowatt you might recognize as a unit of power. So what a kilowatt hour is the integration of power over time. So power, we haven't talked about this yet, but power is the energy per time. So when you're talking about power, you're talking about energy changing or energy moving. And in order to quantify that, you need this concept of power, and the dimensionality of power is how much of that energy moves per unit time. An hour here, in this case, is also a time, right? So when you take this dimensionally, you say, well, a kilowatt hour is a kilowatt times hour. Those times end up dividing out. So a kilowatt hour is just kind of a weird unit of energy. It's just like a joule would be. In fact, a kilowatt is a kilojoule per second. So if we take a kilojoule per second and multiply that times an hour, we end up with units that don't divide out. We have hours per seconds. But that's still a perfectly valid dimensionless number. And we end up with a perfectly valid unit of energy, even though the times don't end up dividing out in terms of kilojoules per second times hours. So again, it's an odd unit, but dimensionally speaking, it's just energy. So I'm just trying to give a few examples of how knowing the dimensions of variables make it clear what some of these weird, obscure units might mean. Degree day is another one that I find kind of weird, so I thought let's play with this one a little bit. A degree day is telling you something about how a plant might develop over time as seeds germinate and as it starts to grow, that sort of thing. That's a variable we use a lot to start to predict when we're going to see plants emerge. Well, what's degree day mean? That's a weird unit. Well, we talked about degree being a temperature with dimensions of theta. We talked about days being a time. So degree day is degree times days, and it's a time integration of temperature, so a time accumulated temperature, or a theta times capital T. That still doesn't get us all the way there, in my head anyway. It's like, what does that mean? Well, let's remember what temperature is based on specific heat and mass. If mass and specific heat are constant, then that temperature, that capital theta, is something like energy per mass. It's about a density of energy in the system. So if we multiply that dimension times time, and a time integration of that, we end up with energy time per mass. Well, that's energy time. That's time accumulated thermal energy. So it's just a way to get after how much energy the system has over time. And that sort of explains to me, oh, that makes sense now. It's like, well, I don't know how to think about that in terms of temperature, but understanding how much energy is available to a seed, to a plant, and being able to use that to predict the development of that plant, that makes perfect sense. So these are just a few examples of ways that I've found that dimensionality has helped me understand what variables mean. So next we're going to talk about how to format dimensions and start talking about the whole